Hello everybody and welcome to this presentation. I am Mohamed Al Lawati and my supervisor is Professor Alan Lynch. And today we're going to discuss some control methodology for a quadrotor carrying a slung load. One of the most appealing applications of having a slung load system is for load transportation. However, in the literature there exists another design which utilizes grippers. Grippers come at a cost of increased inertia and the need of more number of actuators. This limits the maneuverability and also limits the load size. The slung load system, on the other hand, does a better job and also defines a challenging motion control problem. We consider a quadrotor carrying a simple pendulum that's pivoted at the center of mass of the quadrotor. And our control objective is to enforce the tip of the pendulum to track a reference trajectory. Such a system possesses complex dynamics, and we take the approach of partitioning the dynamics into, first, pure rotational dynamics of the quadrotor, and the second part is translational dynamics of the quadrotor plus the pendulum dynamics. And for the second part, we are going to refer to it as TP dynamics. Let's now further zoom in into the details of each set of dynamics. The input for the pure rotational dynamics are the thrust and body torque, and the states are Euler angles and body rate. For the PT dynamics, the input is a pure force vector, and we distinguish between two sets of states. The states belonging to the point mass are position and linear velocity of the quadrotor. The states belonging to the pendulum are angle and angular velocity of the pendulum. For the control design, we take the approach of a nested control loop. The outer loop controls two quantities, the pendulum position and the yaw angle. The inner loop, on the other hand, controls another two quantities, which are roll and pitch of the quadrotor. It's worth mentioning that the TP dynamics are fully immersed in the outer control loop, whereas the pure rotational dynamics partly belong to the outer loop and partly belong to the inner loop, as we are going to see next. Let's now design a controller for the TP dynamics, with the objective to enforce the pendulum to track a desired trajectory. We take the approach of output tracking. However, we find that the relative degree is not well defined for the PT dynamics. Therefore, we apply the dynamic extension algorithm and we find that the algorithm converges after two iterations. This control design gives us two useful quantities. The first quantity is reference signals for roll and pitch that are going to be used for the inner loop. And the second quantity is the thrust. And the thrust is equal to the norm of the force that's applied to the point mass. We now switch to the control design for the pure rotational dynamics. And as we said earlier, the pure rotational dynamics are split between the inner loop and the outer loop. The objective of the inner loop is to enforce pitch and roll angles of the quadrotor such that the force that has been designed using the TP dynamics is achieved. And the objective of the outer loop is to control the yaw angle such that it follows a user-defined trajectory. Now here also we use an output tracking controller, and the relative degree is well defined with the output being roll, pitch, and yaw. This control design generates body torques, and together with the thrust that has been generated with the previous control design, we have fully defined the input of the system. Here, I want to briefly talk about the concept of flatness as an aside remark. Roughly speaking, a flat output is a quantity that all states and inputs of the system can be written as a function of. And a system that has a flat output is called a flat system. Now, what this theorem says basically is that under a certain dynamic feedback structure, a system that is flat can be dynamically feedback linearized and vice versa. Now, this picture represents the structure of the overall system. This part here represents the outer loop, and this part here represents the inner loop. The outer loop generates thrust, desired roll, desired pitch, and the inner loop generates body torque. The user has the freedom to specify the desired pendulum position and the desired yaw angle. Here we are going to see some simulation results where the desired pendulum trajectory has been set to a figure 8 and the desired yaw trajectory has been selected to be a ramp signal, which means that the quadrotor is asked to rotate about its third axis indefinitely. Here in the upper part, we're going to see an animation of the motion. And here we're going to see some plots. The red curve would indicate the reference signal, and the blue curve would indicate the actual trajectory. This plot here is for the pendulum's X position, pendulum's Y position here, and pendulum's Z position here, and finally we have the quadrotor's yaw angle. So let's now start the animation. As we can see that the pendulum tracks its desired reference trajectory, and the yaw angle also tracks its desired reference trajectory. Now here we are going to see the same animation, but now we are going to see the input signals rather than the output signals. So this plot here represents the thrust in Newton. This plot here represents the first body torque, second body torque here, and finally the third body torque. So let's start it. The thrust varies up and down about a certain value, and that value is the total weight of the whole system. And in steady state, these torques are not actually zero, but they oscillate very gently around zero so that the desired roll, pitch, and yaw are achieved. This brings us to the end of the presentation, and thank you for attending this session. And if you have any questions, I'll be more than happy to answer.